All right, so last log video. So as long as the notes were, the videos actually aren't that bad. All right, so here we have a comparison of the exponential and the inverse log of that. So 2 to the x, 2 to the first power is 2, 2 to the second power is 4. So our inverse of that then is log base 2 of 2 would have had a power of 1. Log base 2 of 4 would have had a power of 2. We just swapped the x's and the y's, which graphically means it's flipped across the diagonal. All right. Now, what was a horizontal asymptote on the exponential graph becomes a vertical asymptote on the log graph. Now, log graphs, if the b-value is greater than 1, we get an increasing graph. If the b-value is a fraction, we get a decreasing graph. And that's because the exponentials do the same thing. If instead of 2, I have 1/2, we get a decreasing graph. Now, another nice thing is when you're looking at multiple log graphs, which this was a horrible 1073 question, the higher the base, because 2 ln is like 2.71828, and then log base 10. Log base 10 starts getting close to the x-axis a lot faster than the other two because its base is a lot bigger than the other two. One of the ways, though, to tell what the base number of a log is, like when you have to compare two graphs, it looks really weird. But if we take the horizontal line, y equals 1, we can see I cross about there, I cross about there, somewhere in there. All right, so when y equals 1, this is log base 2 of what equals 1. The what would be 2, which is the base. So this y equals 1 line is the what's the baseline. So the log base 2 graph hits it about 2. ln hits it a little before 3, 2.7. And then the log graph hits it around 10, as it should. So, little weird way to think, but if you do have to compare multiple log graphs, this is actually the nicest way. And it'll work even if you have the b values less than 1. They'll all start up high and come down, but they'll cut in between 0 and 1 on that line. All right. We said graphing the function. I mean, we can, but all right. So log graphs, I can't take the log of 0 or of a negative number, but I can take the log of 1. A number raised to what power is 1 is 0. So one of my key points is the point 1, 0. Another one of my key points is when I put the b value in. In this case, 5. So when 5 is the input, 5 to what power is 5? 1. So just like I was saying before, that y equals 1 line tells you what the base value is. Now our x inside, we've got no horizontal shifting. So our asymptote is here. At x equals 0. So our graph would come down here and hug that vertical asymptote and then shoots off on the right. So there's our rough graph with the key points. Now our domain. The domain of this graph is the range of the exponential. So you look at the graph, I have an asymptote, I have nothing before it. So this is a limited or restricted domain. So the domain of just an unshifted log graph is from 0 to infinity. The range, though, is the domain from the exponential. The exponential, I can plug in whatever I want. So on the log, I can get values out of whatever I want. And then we had our asymptote there, x equals 0. So this leads us into, yes, we can do transformations of log functions. So a log base b of x plus c plus d. All right, so works the same way we did before. I just rewrote it here with my things. A is our vertical stretch factor outside the log argument, plus d is our vertical shift. Then the x minus c, if we c minus c, we're going to the right. If we see x plus c, we're going to the left. The graphs can also be reflected. So if a is negative, it's reflected about the x-axis, which is an up-down flip. If we have a negative inside, this means our domain gets flipped. I'd have to put negative x values in there to counteract the negative in there. So it means the graph, instead of being on the right, will now all be on the left, all the negative x values. And that's the reflected about the y-axis. That'll go left, right. And just like the exponentials, we don't have a horizontal compression or stretch factor because that number can be finagled outside. All right, so now we're given this ridiculous thing, and we're asked, what's the vertical asymptote? So let me answer the bigger question. What do these numbers do? All right, so our a value is -2. So the negative means we're going to flip. And this is outside, so we're flipping y's. Positive y's for negative y's. So I call that an up-down flip, which is called across the x-axis. But I don't like this because then you see x and your brain usually is like, oh, left, right. No, over the x-axis, across the x-axis. And then the 2 is going to be a stretch. So after it's flipped, then it's going to double all the y values. So 2 means vertical stretch. Our x plus 4. So remember, inside lies, it's inside parentheses, inside the function. Looks like +4, which would be right, so it lies, so this is going to go left 4. And then at the end, our +5. This is going to shift up 5. Now, when we're thinking about what all these things do to the graph, we have a vertical asymptote. If I stretch everything twice as tall, if I stretch the vertical line up, it's still a vertical line in the same spot. If I shift everything in the graph up 5, the vertical line is still in the same spot. So the only thing that will actually mess with the asymptote, with the domain, is if it's inside the function, our left and right shifting. So our original graph has a vertical asymptote at x equals 0. This graph is shifted left 4, so our asymptote is going to be at x equals -4. But we can also get this by taking our argument and setting it equal to 0. All right, last one. Find a possible equation for the common logarithmic function graphed here. So they go to the effort to tell us common log. That means log base 10. Also, we see that this graph is going through 0, 0. And it looks like also possibly negative 1, 1. But we see up here, our vertical asymptote is at x equals negative 2. So if I kind of undo what I did on the previous one where I set the argument equal to 0, I'm going to add the 2. So x plus 2 would give us a vertical asymptote of x equals negative 2. So I know I need to see log of x plus 2. Now this is also, it's a decreasing graph instead of an increasing graph. So to get that positive y for negative y flip, we're going to need an a value that is negative. All right, so up, down, flip means a is negative. All right, so I don't know what my a value is, and I don't know what my d value is. But I have 2 points on the equation on the graph, and I pulled my vertical asymptote, so that gave me my c value. So I can, using those 2 points, like work out and figure out what the heck this thing is going to be. It ain't going to be pretty, but we can do it. So this is our f of x, and then we're going to use the points 0, 0, and negative 1, comma, positive 1 to finish out the equation. So f of 0 is a log 0 plus 2 plus d. All right. So f of 0 is 0. So I have 0 equals a times the log of 2 plus d. So the log of 2 is some ugly number. So now let's go ahead and do our other point. F of negative 1, which equals 1. I have a log of negative 1 plus 2 plus d. I still don't know a, but I know now that this is the log of 1, which that should ring like a little bell. Wait, log of 1 was one of our specials. 10 to what power is 1? 0! So we know our d. So this is 0. A times 0 is 0. So we get d is 1. Ha-ha! So over here, we can shoehorn in that 1. So 0 equals a log of 2 plus 1. And now we'll continue solving. We minus the 1. So now I have negative 1 equals a times the log of 2. Log of 2 again is a number. A times a number, I can divide by the number. And I could crunch that up as whatever decimal it is, but I can also just leave it as -1 over log 2. So our actual function will be -1 over log 2, which matches that thought we had earlier that the a value had to be negative to make it a decreasing graph. Common log of x plus 2 with a plus 1. So just using the same principles we used with the exponential graph or when we were given points, we can do the same thing for any type of graph. If I know the basic equation and I know as many points as I have unknowns, or I have pieces of information to lead me to those unknowns, I can find everything, I can determine the full equation. That concludes the ridiculous videos on logs and exponentials. Yay!